Okay, that is our degradation or restorations model. Now let's discuss about the phase 1 or the condition 1, where we assume that our model here is free from degradation factor or from the degradation functions there. We only assume that our image G is affected with noise. Okay, in other words, we just assume that we have some hardware or some camera where that camera is free from blurring function or degradation function. The the degradation factor that affected our image G is only come from the noise. Okay, the reason why we do that assumption is because we just try to do some just assume that we have some hardware where actually that hardware is free from blurring function, and the one that affected your image G is only come from the noise or come from this additive noise. Okay, so if you talk about this, that is what happened at the phase 1 or condition 1. Later we will discuss the phase number 2 and phase number 3, where in phase number 2 or condition number 2, the image itself or the model itself is free from noise, but the cause of your image is only come from the degradation factor that affected your image G is only come from the degradation function. And then the third condition or the phase number 3 later, where we the image G, okay, the degradation factor that affected your image G is come from both degradation function as well as noise. Now in phase 1, just assume that our image G here is only affected with this noise, meaning that the image itself is free from degradation function or which is come from blurring factors. Okay, just assume that. So from this equation there, as you can see, it can be simplified. The block from here, once you cancel this block, of course you have cancelled this block in condition number 1, you have cancelled this one. Okay, when you have cancelled this one, and then the block can be simplified as this one. Of course, if you write the equations, now the how to express the degradation image G now is only equal to our F plus our eta there, which is represent this noise. So if you talk about the expression in frequency domain, then it's almost similar with the spatial domain. Okay, just change it from the small letter into capital letter uh, to represent the frequency domains. Okay, let's go back to our slide. Okay, this is the first condition or the first phase where we assume there's no degradation function. Okay, the one that affected your image G is only come from the noise. Okay, image with noise only. So this is the expression that I have shown before in my whiteboard there. Okay, from the main expression, we can simplify with this equation or this expression, because now there's no blurring function anymore. So that's why to define your G, the degradation image G, then actually is equal to our input image, our ideal image F plus our additive noise. Okay, from here again, what actually our main objective is actually we want to obtain, actually the main purpose of restoration, we want to obtain our F, again our F, but of course we cannot achieve F. That's why at the end of restoration we notated with image with some notation which is F head. Okay, why we still call F head? Because it's a predicted value of our F. So that's why when you apply the restoration again, we want to have a best restoration process where you can obtain our F head as close as our F. So from this equation, if you want again, if you want to find f heat, okay, if you want to obtain our f heat, which is actually should be, you know, we want to, if you talk about the ideal f heat, then you must achieve your f heat similar to your f xy. So after you assume that there's no degradation function or blurring function h, then the equation or the definition of your affected image G can be simplified into just f plus, you know, your noise there, your eta noise there, eta that represent the noise. So if I want to get my f from this equation, then okay, if you see the equation, since it's only a plus operation, then you can, you know, you can just, okay, you can just, you know, take your G, because that is the one that we can access, okay, your gxy, and then you just directly can minus your, sorry, that's I try to, you know, write back this one again, because the because the areas there is not good there. Okay, let's try to write it here. So again, our objective for restoration, we want to obtain our f heat which is close to our f. If you remember, this is our main objective for image restoration. Then if you can get your image f heat, you know, equal to your f, then that should be perfect. Okay, that is the ideal thing that we want to do. If we can get 100% similar between f heat and f, then that should be good. Because but in practically, it's very difficult to get that. That's why we notated the output of restoration if f heat, which is the predicted value of your f. So that's why the image restoration is the process of to achieve f as close as f heat, to produce the f heat where the f heat should be close to your f. Okay, so from this expression, after you have simplified this expression by you know, removing the blurring or degradation function, because just assume that our hardware is free from that cause of degradation. So if you talk about your, to obtain back our f heat, and you said your f heat is equal to your f, that is the perfect restoration that you can do. If you can get that, that is a perfect, the ideal one. So from this equation, again, we know that the one that we can access is this one. This one is the one that you are received from your hardware or received from your digital camera. So then you can, of course, that one can be accessed. So to obtain that, then you can, you know, manipulate that equation. You just put there, if I want to get my f, then f should be equal to my G minus my eta xy, which is the additive noise that in this model, which is this one, the noise. Okay, so that is what we can do. However, as I have been discussed in this statement, we cannot simply generate the, okay, we cannot do this operation. Why we cannot do this operation? Because in general, this is noise. Okay, when we talk about noise, noise is always in form of random signal. Okay, we call it as a random signal, because we cannot estimate the noise. So in other words, because it in form of random signal, you cannot simply generate the approximation of noise and simply, you know, doing this expression. In other words, okay, in order for you to get fxy, okay, you cannot simply take your G and minus with your noise. The reason is that this one is fixed value, but this one is random value. Something random is very hard to, you know, it's very hard for you to estimate or to do approximation, because when you repeat the same process again, you just imagine when you write a program, when you call some random number or random function to generate random number. Once you run that code, and the next time you run the code, you will realize that the random function will generate the different value because of the random behavior. So same goes to this equation. When you want to do the simple operation of subtraction here, is not simply, you know, just subtract between the G and the noise, because noise is in random signal. It's hard to estimate, and of course because of that random signal, you cannot just generate the approximation and minus and you cancel each other. Then you can obtain F, where your F now, once you obtain your F, it should be perfect, because F is actually is the what that you want. Okay, because at the end what you want is your F head, and if your F head is close to your F, in other words, you already get the original F, that is better. But it cannot be done by simply, you know, take your G and minus your noise, okay, in this process, because the noise is cannot be, you know, cannot be simply generate by do some approximation of noise. Okay, that is the behavior of the noise, because noise is in random signals. Okay, before we go further about this thing, okay, again I will like to highlight here, okay, noise is a random signal. So if you have a random signal, something is unpredictable, so you cannot simply do the subtraction operation just to cancel between your degraded image with the additive noise, so you can get your F, where now if you can obtain your F, which is the ideal image, which is free from anything, then you achieve your objective to obtain your F head. Okay, but that simple operation cannot perform in this. Okay, it's not appropriate to do that way because of the behavior of the noise, which is in random signals. Okay, now before we go further about, okay, about this process, now let's discuss about the characteristic of random signals. Okay, because this is very important before we go to the next discussion. Otherwise you don't you cannot imagine what happened, or because you don't have any fundamental knowledge about random signal.